Let's get started with PyTorch. To import PyTorch, we'll do import torch, and we also console log the version of PyTorch that we're using. So here we see that the version of PyTorch is 1.5.0, which is the latest version of PyTorch. Let's start with the basics. So let's start with defining a tensor. So for example, A is a tensor that consists of a scalar value, and a tensor is just a generalization of a matrix or a vector or even a scalar. So for example, here A is a tensor which consists the element 2, and it consists a scalar, which means if you look at its shape, it's going to return an empty set because it does not have a dimensionality. So let's now move on to vectors and define a tensor with a single dimension, which is B over here. So there are, if we call the b.shape, this returns a size. It basically has one dimension which has 3 elements. So another way of knowing how many elements are there in a tensor, we can just do numl or num elements, and it tells us that this tensor has 3 elements. So an easy interpretation of the dimensionality of a tensor is just to call the len of your the tensor. So for example, this, and now this returns a value of 1, which basically means that this tensor has a dimensionality of 1. And if we, for example, call the len a.shape, which was defined over here, let's see what this returns. This returns 0, which means it does not have dimensionality, or it's a scalar. This one, B has a dimensionality of 1, which means it's a vector. And now let's define a matrix real quick. And we see that C is now another tensor, or basically a matrix. And why? Because this has a dimensionality of 2. And basically that means it has a number of rows, a number of columns, width, height, whatever you want to call it. There are higher dimensional tensors that you can define. So for example, an image is normally a 3-dimensional tensor, which usually represents a channel, like a red, green, or blue channel, the width of an image and a height of an image. But we will come to that in later sections. So now that we have tensors out of the way, let's look at a real quick application of using these tensors and using something called as autograd and why it's useful. So let's start with defining a variable, and let's give it a value of 10. And in addition to initializing this variable or this tensor with a value of 10, we are now passing in an argument called requires grad. And basically this means that we can compute gradients on this tensor, and this will become clear in just a moment. So now we have our x defined. Now let's make another variable. Let's call it z, or let me call it loss. And let's define loss as, x square, let me think, minus 8x plus 16. And if you think about it, the value of this function is minimum when x equals 4. So 4 to the power 2 is 16, minus 32 is minus 16, plus 16 is 0. So if you were to solve it using linear algebra, then you would get the value of x equal to 4. But now let's try to solve this using stochastic gradient descent. So loss is a function of x, and if we compute gradients on loss with respect to x, we get a direction of gradient ascent, which means the direction to move x in such that this value is increased. However, we want to minimize the loss, for example, then we move in the direction opposite to the gradient. Again, this will become clear in just a moment. So let's run this and let's look at the value of x, which is 10, and loss, which is 36. And this is clear. But now when we look at the loss representation here, it tells us that it's a tensor with value of 36, which is what you get when you substitute x with 10. But you also see this gradient function, which is something called as add backward. So this function holds, let's say, a reference to the variable that was used to calculate this loss. So when we are calculating gradients in PyTorch, it will look at this function and track backward to find which variable was used to compute this loss function. And when you compute gradients, it will compute gradients on those specific variables that were part of this computation graph. So this is the dynamic computation graph terminology which PyTorch uses, which basically means that PyTorch computes this computation graph dynamically based on the code you write, which is very handy, and we'll cover this in more detail in later sections. So now imagine if you want to find or minimize this loss over here. And to do this, it's very simple. You will call something called as loss.backward. And what loss.backward does is it will look at this function and then compute gradients on x. So let's do that. And to look at what gradients were calculated, we can check this out, and it tells us that the gradient of x is equal to 12. So how would you use this? How would you minimize the value of your loss? Well, one way is to update the value of x such that it is reduced. And of course, usually we do not directly multiply with the gradient value, and therefore this parameter, which is known as learning rate, such that we take many steps towards the minimum loss area. So we can do this, and when we look at x, we see it's now 9.88. But another way of doing this is to define an optimizer, and to do that we can do torch.optim. Let's say, and we can call this module and define our optimizer as an object of, for example, stochastic gradient descent, and pass it the variables that it can change in order to minimize the loss function. So we pass in the model parameters, which in our case is just this x tensor, and we pass a learning rate, which was defined over here, and therefore now this becomes a parameter of our optimizer. We have our optimizer, which has our model parameters x and a learning rate parameter, which we set to 0.01. So let's see what happens when we do a complete loop of stochastic gradient descent. So we recompute our loss, and loss at the moment is 36. The value of x is 10. And let's do a backward step on our loss to compute gradients on x. So to do that, we can do loss.backward. and then do one step of stochastic gradient descent. So to do that, we just do optim.step. Optimizer. And when we look at our x again, you see that its value is changed back to 9.88, which was also what we obtained when we did this manually. But now we did not have to do this manually. Now this optimizer module did this for us, and it received as arguments the parameters that it could change, and that's how it was able to change this value. So this is how you would do one loop of stochastic gradient descent. Let's just look at the value of loss again, just to see it actually worked, and we see that it reduced from 36 to 34. So now finally, let's write a loop of stochastic gradient descent to minimize our loss. So again, loss is just defined as this loss. But before we do loss.backward, we have to zero out the gradients, and that's because PyTorch doesn't zero out the gradients when it calculates gradients. If you don't zero out gradients, then the value of these gradients are appended or added on to the previously calculated gradients. So just to show that real quick, let's see. If we do x.grad, this is equal to 12, which is what we got from the first time. And now if we do loss.backward and do x.grad, we see it's about 24. It's not exactly 24 because we changed the value of x, and therefore the gradient value has also changed a bit. But because we did not zero out the gradients, it was appended on to 12, which was calculated previously, and that is not what we want. We want to recompute gradients every time we take one step of our stochastic gradient descent to minimize loss. So to do that, we have to call this function called zerograd, and you also see from the documentation it tells us that this function clears the gradients of the tensor on which the gradients are being calculated. So we do that, and then now we do loss.backward, and finally optimizer.step, and this will run 1,000 times. So finally we can then print loss, and we can print our x. So now it ran 1,000 times, and we see that the value of x converged to 4, which was also the value of x that would minimize this expression without actually having to calculate it. We just ran stochastic gradient descent a number of times, and we were able to find a value of x that minimized our loss function. So this was a getting started tutorial on PyTorch. In later sections, we will look at more applications.